Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors Chapter 9 Quiz 2 Review Solutions on algebraic limits. For these questions, we're trying to find limits algebraically if they exist or explain why they don't. So our first course of action, unless we see common factors that we can very clearly cancel out, is just to plug in our x value that x is approaching, at least if we have a non-piecewise function. If it's a piecewise function, we have to do something else, but for non-piecewise, we can start by plugging in the x value. If we do that here, we end up with 0 squared over 2 minus 2 times 0, which is just 0 minus 0, or 0. So since we're getting a constant number after plugging in on a non-piecewise function, that means that 0 is going to be our limit for this one. For this problem, we're trying to find limit as x approaches 3 of this rational function. Now, it looks like I might be able to factor, but on closer examination, I really can't factor x squared plus 9. So we might as well just plug 3 in here. If we do that, we've got 3 squared plus 9 over 3 minus 3. So that's 18 over 0. Since we have a number that is not 0 divided by a number that is, that means we're dealing with a vertical asymptote for this. So that's going to be dne. The limit does not exist here. To find the limit algebraically on this one, you could start by plugging in -6. You will see if you do that you end up with 0 over 0. If you get 0 over 0, that means do more work. And by the way, you're not going to write equals 0 over 0 because that would be a calculus no-no. At the most, you could say like arrow, 0, 0. But anyway, since we see that we have at least a 0 in the denominator, and that we can factor the numerator, it's not a bad idea to just start by factoring this thing. So up top, two things that multiply to 18 and add up to 9, that would be 3 and 6. So we can factor the numerator like that, x plus 3, x plus 6. And now we see these x plus 6's actually cancel out. So that's what was giving you the 0 over 0 when you just plugged -6 in. But now we're just taking the limit as x approaches -6 of x plus 3. And since we've crossed out the problem here, we can just go ahead and plug in -6 now. Now, you notice that you have to keep writing limit until you actually plug in a number. Once you plug in this -6, now we're just dealing with a straight-up function value, which happens to correspond with the limit. So this is just -6 plus 3, which is a limit of -3. For this problem, we're trying to figure out the limit as x approaches 3 of this piecewise function. Since 3 is a border value, that means we have to find the left and the right side limits as x approaches 3. So to find the limit as x approaches 3 from the left side, we use the before rule that deals with the x values that are less than 3. So essentially you're plugging 3 into the -2x plus 7 part of our piecewise function. So that's going to be -6 plus 7, which is just 1. Now we find the right side limit as x approaches 3 from the right by plugging 3 into this after rule, the rule that deals with the values after x equals 3. So that's going to be -3 plus 4 if I plug that in, and that also comes out to 1. Since 1 equals 1, since the left and the right side limits agree, that means the overall limit as x approaches 3, the two-sided limit, is going to be 1. For this problem, we're trying to find the limit as x approaches 1 for this piecewise function. Since 1's a border value, we check the left and the right side limits at 1. For the limit as x approaches 1 from the left, we're using this first rule for values that have x less than 1. So essentially we're just plugging 1 into -x minus 5, so that's -1 minus 5, giving us a left side limit of -6. For the right side limit, we're now just going to plug 1, the border value here, into this second function. So that's -1 squared plus 2 minus 1. Well, we've got two -1s and a positive 2, so that adds up to 0. 0 and 6, -6 rather, are not the same thing. Left and right do not agree. Therefore, the limit as x approaches 1 does not exist. For this problem, we want to find the limit as x approaches 3 of this absolute value fractional thing. So to do this, first I'm going to let this expression equal f of x. Now the key on these, and I'm doing this so that it's easier to refer to this clunk of stuff here. The key on these is, since its absolute value, which is secretly a piecewise function, the key is to write it in piecewise function form. So I'm actually going to rewrite this as a piecewise function with a border value of 3. I'm choosing 3 for my border value because 3 is what zeroes out the stuff inside the absolute value. So 3 is what separates the x values that make the stuff in here negative from the x values that make the stuff in here positive. And we need basically 2 different rules to accomplish what absolute value does, which is to just make everything positive. We're going to have one rule for the things that make x or make the absolute value stuff negative, and then we'll have another rule for the things that make the stuff inside absolute value positive. Now, if I plug in an x value that makes absolute value negative inside, I want to force it to be positive by multiplying it by -1. So I'm going to basically just replace this absolute value of x minus 3 with negative parentheses x minus 3. Since there's already a 3 here, I'm going to write -3 parentheses x minus 3 all over x minus 3. So this simulates that absolute value property of making negative things positive. Next, if I'm plugging in x values that make the stuff inside here positive to begin with, well, if it's already positive, I mean, if it's not broke, don't fix it. We're just going to drop the absolute value and replace that with a normal parentheses now. So here's our rule for where the stuff inside comes out positive. We just don't change anything. Now, if you were to plug in 3 right away here to try to find some limits, you would just get 0 over 0 for both of these. So that means we have to take one more step here and reduce these fractions. We've got x minus 3's in both of them that can cancel. So I can rewrite my top rule here as -3 and the bottom rule as just +3. And now if I want to find the limit as x approaches 3, since 3 is a border value, I have to consider the left and the right side limit. The left limit, the early limit, the before limit here, is going to just be this constant of -3. And now the right side limit as x approaches 3 is going to be the second rule, just a constant value here in this case of 3. Since -3 and 3 are not the same thing, left and right limits don't agree, so the two-sided limit at 3 does not exist. On this problem, we're trying to find the limit as x approaches -infinity of this polynomial. Since we're going to an infinity, we can ignore these slower growing terms. So I'm just going to forget about the 7x squared and the -3, and I consider only the 2x cubed. Now note that you can only do this forgetting kind of thing if x is approaching infinity or -infinity, because we're talking about long-run behavior at that point, and we don't care about what these slower growing things are contributing. If x is approaching a constant, then by all means you have to consider all these other things. All right, so now we just have to plug in the -infinity. Since we only have a single x here, plugging in an infinity, we should be able to deal with that. -infinity to the third is -infinity. 2 times -infinity is still -infinity. So -infinity is our final limit on this one. For this problem, since x is approaching infinity for this limit, we can ignore the slower growing terms. So 12x to the 5th is our champion in the numerator. In the denominator, we're just going to keep the 4x squared. Everything else is just slowing us down. And now I can go ahead and reduce these. 12 over 4 is 3. X to the 5th over x squared is x cubed if we subtract those exponents. So I've just got 3x cubed, limit as x approaches infinity. And now I can plug that infinity in. So that's just going to be 3 times infinity, which is just infinity. For this problem, we're trying to find the limit of x approaching infinity of this craziness here. So since we have a fraction and we're going to infinity, we're going to choose our champion and ignore the slower growing terms. In the numerator, we've got a lot of really quickly growing terms. This is a very high degree polynomial. We've got a factorial term, we've got an exponential term. Out of these 3, the factorial actually grows the fastest. There's actually only one thing faster than factorial growth. And that one thing that's faster happens to be this x to the x down here in the denominator. X to the x is the denominator champion. So I'm going to rewrite this as -x factorial over x to the x. And now this is a bottom-heavy function. We just said x to the x outgrows factorial growth. Since it's bottom-heavy, that means this thing is just going to go to 0. On this problem, we want the horizontal asymptote or totes for this function. So to find any of those, you need to take the limits as x approaches infinity and negative infinity. Often they give you the same thing, but sometimes you get something different. So we always at least mentally consider both of them. Let's do positive infinity first. Since we're taking a limit to infinity, that means we're allowed to ignore the slower growing terms in the numerator and the denominator. In the numerator, the fastest growing thing here, the champion of the numerator, is this exponential term, 4e to the x, outgrows polynomial and logarithmic growth by a long shot. In the denominator, 5e to the x is the fastest. Again, we're outgrowing a polynomial and a constant, which isn't even really in the running. So we end up with 4e to the x over 5e to the x if we just choose our champions. And we can actually cancel out those e to the x's, giving us just 4/5. So that means as we move to the right, positive infinity, we have a right horizontal asymptote of y equals 4/5. All right, now we're going to consider the limit as x approaches negative infinity. And again, usually you end up with the same thing, but because we have an exponential function in here, we're going to look at negative infinity on its own, because negative infinity and positive infinity do different things with exponentials. Specifically, exponential functions, as you move to the far left, decay towards the x-axis, towards 0. The limit as x approaches negative infinity of 4e to the x is 0. Same thing with 5e to the x. So those are no longer the fastest growing functions in the numerator and denominator. In the numerator, we now have to choose between 9x to the fourth and ln of absolute value of x. And we've got this absolute value here, so we are allowed to plug in negative numbers on the way to negative infinity. But it doesn't matter. Logarithmic growth is so slow. Polynomial growth overtakes it in a heartbeat. So 9x to the fourth is our champion in the numerator. In the denominator, it's down to negative 13x to the 100th versus the constant 12. Well, this is no contest either. Negative 13x to the 100th wins down there. So here are our champions for the negative infinity round. We can reduce this a little bit if we wanted to, but honestly, we can very quickly see this is a bottom-heavy situation, so 0 is going to be the horizontal asymptote for this. So a left horizontal asymptote at y equals 0.